Okay, this is the third and final section of the intense review for biology and general science. We packed in biology in the first two sections of the video. This is just going to focus on the science reasoning or general science. I'm going to go pretty fast through most of this. There really is no better way to think about this and learn this stuff that's from science reasoning than the science reasoning classes, the ones that you did. And the reason I do intense reviews is a couple of things. One of them is because you can really only hear something for the first time once. And so I always try to design another lecture, even if I'm really repeating the same thing, which largely I am, right? Because there's concepts that you have to know them, and you have to know them in a certain way. And I can't vary my style much. But it's definitely different when the pictures are different, because if you're taking this class and you took those classes, you now have two sets of pictures and you have two sets of worksheets that are different, and you're practicing on something you haven't seen before. And all of that is important. This is the one instance where I don't know that I could actually benefit you by redoing that science reasoning 1 lecture. There are certain elements of it that I will call out that I want you to maybe think of some certain things again, or think of something differently, because the other reason I said just a minute ago, there's 2 reasons I do intense review. The other reason, the second reason, is that the test does evolve over time. And when I designed my curriculum in the first place, I think my sound went out for a second. I'm going to repeat what I said right before that, just in case. Let me plug my computer in real quick too. So the second reason, in case this didn't record, that I do these intense reviews is to kind of bring some updates. The test evolves over time. It gets harder. The questions get deeper, or they get more advanced, and occasionally questions surface over different content that wasn't really tested earlier in the span of the test. And there are a few of those things right now. Again, just like I said earlier in this series, I am about to redo the curriculum because it's a year old, and I always redo it at about a year. So right now it's March of 2019. If you're seeing this in March or April of 2019, you probably saw the old curriculum, and there probably are a few things in here, just like with the first 2 videos, that are updates that you haven't seen or didn't see in the same manner, or didn't study quite as intensely as maybe now you would want to. If you're seeing this a year from now or a few months from now, you probably have the newest of everything because it is updated at that point. Definitely go back. Unless you feel very, very good about General Science 1 or Science Reasoning 1, definitely go back to that lecture. This first 1, 2, 3, 4, the first 4 pages of this part of the packet, and also of the packet that I gave you for Science Reasoning 1, this part I'm not going to re-explain, and I'm not going to do other examples. I am going to clarify a couple things, but if you don't feel like you are 100%, A+ quality on the stuff that is on this page and then the 3 pages following it, so 1, 2, 3, and 4. And actually, we are missing some stuff here. I just realized. So there's also, that is so weird. So something went wrong with the scan right here. So on the page that says improving an experiment, we're missing quite a bit there. I believe we're actually missing 2 pages. We're missing half of this page. You're missing the B, C, and D that go with this example. And then there's another page that's got some other examples. Not a big deal. This getting left out of this packet doesn't matter because you already have these 4 pages. These are the 4 pages that are not new at all. They're completely, I printed them from the class that I already taught you. They're exactly the same. So we won't worry about that. You'll just pull that from your other packet. And I think most of you will probably go back to science reasoning 1 to ensure you remember all the stuff that's in the very first part of that class. Science reasoning is 7 of the 47 questions, and then biology and chemistry, which is life science, is 8. And what's always frustrated me a little bit as a professional with this particular subject matter is that the biology, in particular, the life science, is spread really thin. It tests so many concepts, so many different things that you have to know to be able to answer the questions that you may get, because although you're only going to answer 8 questions, those 8 questions could be over any number of a possible 100 different things. That's a little bit of an exaggeration, but not too much, that you would have to know. So I'm not making my point as clearly as I'm hearing it in my head. But what I'm kind of saying is there's not a lot of questions on life science, but we have no way to know which ones you're going to get. And unfortunately, they cover a ton of possible domain. And I'm going to start to integrate this into all of my lectures as I go backward and start re-recording curriculum. There are definitely going to be things, lots of things, many things that you learned and that you really kind of slaved over almost with this program, that you really put a lot of time into, maybe got a lot of frustration from, and worked really hard on studying. And there may be things that I pushed you to make sure you did during the course of your studying, only to get to your test and not see it at all. That is totally part of this whole thing. The test is completely random. Each question gets pulled one by one onto your test as your test rolls out in front of you, and there's no way to know. So for example, I've had situations where I have a student say, I don't want to take geometry, or just maybe they're just trying to hurry in general. They don't have a lot of time. And maybe I push that person to take geometry because maybe that person's trying to score in the 90s and I want to make sure they have everything. And then I will occasionally get an email after that that says, after all that, I didn't get any geometry. I didn't even see there wasn't any geometry on the test. And so sometimes people misinterpret that as that I thought something is on the test and it's not, and they put time into something that was a waste of time. And that's not the case. What happens is there's certain sections that don't have lower limits that you actually don't have to get a question over at all. And then there's some that have limits where you cannot possibly get a test that doesn't have it, if that makes sense. With life science, you are going to see a handful of the things we just went over and the things that you're going back to review from your original 2 lectures. You will not see all of it. You may not get to name a chemical reaction like a replacement or oxidation reduction. You may not see anything about aquaporins. You may not see geometry, off topic, but may not see geometry. We don't know though. And so if you have a pretty high goal, we have to essentially serve the idea of making sure you have everything, because we're not going to know which categories you get a lot of questions in until you're sitting at the test, and I can't do anything to ensure anything at that point. So regarding the life science that we've already done, make sure that you use a combination of the intense review, especially the stuff that's new. And I do feel like I pretty clearly pointed out anything that's new or that's different or that's evolved. I'll go back to this recording and make sure that that's the case. I'm going to do the same thing with science method. There's going to be a lot less clarification. This is potentially and hopefully going to be a much shorter recording than any of the other segments. And just like I said with life science, I'm going to completely not talk about certain things. This is designed to be in conjunction with the lectures you already have and you already did. There may be an occasional exception to this. I may have a student once in a while who's just in such a hurry or on such a budget that we can't do everything, and I might recommend this class in place of the real classes. Usually I would not do that. You need both. So you want to make sure you are combining what you already did with this stuff. A lot of this stuff in this packet is new and it's updated. Anything where I'm asking you questions is new and updated. There is one thing that didn't make it into this packet life science wise, and that was the balancing of chemical equations. Right now, I'm not getting very much feedback that balancing is showing up for a lot of people. But again, it's absolutely in the question bank. It absolutely can show up on your test. It's not gone. The last few times I've tested, I have not had a balancing question. Instead, I've had a question that asks me if something is oxidation reduction or maybe replacement, kind of that thing has been in its place. I'm not going to go through balancing because, again, the original lecture on that was great. It was exactly what you want, nothing more, nothing less. That is in Life Science 2 near the end. So make sure that you go back to that if you're still concerned about that. The questions that I gave you in that packet, Life Science 2, those are the equations you need to know how to balance. To my knowledge, there is not another equation that is not very similar to those ones, to those 4 that are on that little page by themselves. That's what you're going to see. It's a narrow scope. So if you can balance the equations I've given you and you understand the way that they were built, you're good on that. This first 4 pages, or it's supposed to be the first 4 pages, and actually 1, 2, 3, 4. It's actually supposed to be 5 pages, and we have 3.5 of them here. So make sure you go back to your science reasoning folder to get these first 4 pages the way that they're supposed to be. Make sure you understand these examples again. One of the critical things is knowing the steps of the scientific method, and they're right here. I should probably change them from A through F to like 1, 2, 3. So do that if you want to do that. Since it's steps, that kind of goes with numerical better. The problem or topic identification, that's an interesting one. In fact, there's a little bit of weirdness right in this little area. And that's the only thing I'm going to focus on here. I'm not going to read you the steps. You've already read them. You already know them, hopefully. The questions that could be confusing are when they say something like, what does this person do first? And the way that I taught you this and the way that I've emphasized it in the mocks, I'm always talking about research. Well, the reason I emphasize research as being the first step, because it's actually not. The first step is deciding what you even are interested in at all. You can't do research on something if you haven't even picked a topic, and then you can't do research on it if you haven't kind of picked what aspect of that topic you're going to center on. That never used to be an issue because they didn't really put questions in that pocket. Now they're kind of starting to. And honestly, it's just totally practical, real life, logical thinking in this case. It's going to depend on the context that they give you. If they describe to you some type of something somebody wants to know more about. So there's lots of examples I can think of that are from the TEAS. You know, such and so wants to study the effect of sodium on blood pressure, or the effect of a certain chemical that's in fish meat, and that the effect of that on cancer. Or so if they tell you about what the topic is, if within the question it's clear that they have definitely considered and figured out what their topic is, and it's clear that they have an idea of kind of what they want to study, then those first 2 steps are done already. And it's unspoken. Essentially, right here, it says an experiment should always be preceded by research into previous scientific work done on this topic. So basically what I want you to know, you can't do anything, whether it's write an essay or do an experiment, if you haven't picked a topic. And you know from reading class that topics are big, they're broad. So let's talk about The fish example. So such and so, we're going to call him John for spelling's sake. So John wishes to study, and this is a very realistic scenario that has shown up on the test several times. John wishes to study a chemical that's found in fish. You can write this down or not. You can just follow along if you want to. And its effect on human health. That's a very realistic one. It's not word for word. I never do word for word because of copyright. I don't want people to do that to me, so I don't do that to them. But it's very close to that. And there's lots of variations. There's lots of things that are absolutely nothing like this, and they're going to fit this same kind of process. So in this question, they're giving you this as part of the question. The question ultimately is, what should he do first? Or what does he do right now from where we're standing? Obviously, he has thought about his topic and his main idea. Because his topic would be something like, and you could kind of say it's a lot of different things. You could say his topic is fish. You could say his topic is chemicals that are found in food. You could say his topic is human health. It doesn't really matter because we don't know what he thought of first. Whatever came to his mind first before he got more specific about it, and then we see it in its more specific form, that was his topic. So you got to have a very general idea of what you want to study. Obviously, we can see that he's studying humans and the effect of eating certain things rather than studying paper towels and how much water they absorb. Those are two very different topics. So topic, you're never going to be asked to say what a topic of an experiment is. So don't worry about being able to identify that. That would never happen. You can't actually say exactly what the topic is because, like I said, it depends where their thought process started. It depends on what types of things they're wanting to figure out and study. Main idea would be kind of what they're giving you. So he wants to study this chemical that's found in fish that humans eat, and then its effect on human health when humans eat this chemical. So let's say for now, let's say that this chemical is what he's most interested in. He wants to study this chemical, and then its effect on human health is his kind of main idea. They didn't tell us here that he had selected a topic, and they didn't tell us he had selected a main idea, but knowing what those things are, we can obviously see that he does have these things picked out. In this case, the first step, as they're asking for, is right here. We need to find out, has anybody else studied this chemical? Has anybody else studied the effect of this chemical? And that's before. What you need to make sure you know and kind of have memorized in your head is that research is done before the hypothesis is created. So you can come up with a lot of your kind of experimental design before you do the research. You do not want to be selecting a hypothesis, because when you make your hypothesis, you actually do want that to be a semi-accurate prediction of the outcome. And it's okay if your hypothesis winds up being wrong, because the point of a hypothesis is just to have an idea of what you think is going to happen, but then scientifically, we find out what really does happen. As the scientist, if you actually care about this experiment that you're making, you want to make that prediction as accurately and specifically and clearly and correctly as possible. So you do the research before that. You don't guesstimate what's going to happen until you take into account that other people have studied different things about this, and here's what they've found. That will help you predict more accurately what you're going to find. So that's the part I wanted to focus on with this. I'm not going to tell you what the steps are and how they go in order and that sort of thing. You guys know that, and if you don't, that's something you can get very easily from your original lecture. But recently I've started to see, this used to always be the question is, they describe an experiment and say, what's the next step or what's the first step? And even though this is, right at the third step, we always kind of answered that way because they would say first step, but they would also have given us like the content of the experiment, which meant that these two steps had already happened. Now they're starting to actually go backward and ask a question like, Julie wants to do an experiment. What does she do first? Well, in that case, it sounds like she just wants to participate in science. It doesn't sound like she's thought about her topic or her main idea or anything. And so in Julie's case, if she's just barely thinking about maybe conducting some sort of experiment, she can't do research on what's out there because she doesn't have a topic to research. She doesn't have something to click into Google yet. That all sounds really obvious and silly. And so if you're sitting here thinking like, I get this, that's fine. The reason I'm clarifying this is some of you take what I tell you to use and think so seriously. And I appreciate that because I would never steer you wrong. But sometimes people take that so literally that they forget to factor in that something might be missing that should have been there. And then their answer would need to be adjusted. So I'm just kind of clarifying to you. They could ask you for the first step and actually mean it because the actual first step is this. They could also ask you for the first step and give you a topic, but not a main idea. And you know that from reading, you understand what I mean by that. They could say, John wants to study fish. Well, in that case, his next idea is to kind of determine step 2, the actual step 2. What about fish? What do you want to study? Then he could do research once he determined that it's this chemical that's in the meat that he wants to study. So that's all practical and obvious. And if you had never learned any of this, I think that would be fairly obvious to you. But if you've been focusing on research, just don't forget to make sure before you say that they should be doing research right now, make sure they have enough information to do that research. If they don't, then they either need to do step 1, topic, or step 2, what about that topic do they want to study or zone into? Once the research has been done, then the hypothesis can be created. I always get a question, always have on every edition of the TEAS, continue to do. I always get something about the hypothesis. They may get very detailed and say, such and so thinks that when he does this, this, and that, the result is going to be this, this, and that. What is this? That's obviously them describing his hypothesis. They might be a lot simpler than that. They might just say a prediction of the outcome of an experiment is called a what? Or they might ask for this stuff that's right here. A hypothesis has certain properties, and those properties are extremely important to having a hypothesis that fits the scientific requirements. It needs to be testable. You can't have a hypothesis if it can't have an experiment set up that accurately tests it. And it's got to be repeatable, and not just by you, but by somebody else. So you've got to be able to form a clear experiment that isolates that hypothesis with an independent variable that you're going to test. And you have to be able to instruct someone else to do what you just did with it. And then predict. So we talked about this before. Predict is a very good word. Anything that says looking forward and saying, this is what I think my experiment is going to turn out, that's a hypothesis. You can't get to that point, though, until you've picked a very big topic like fish, a very specific topic like a certain chemical and what is its effect on human health. Then you do research on whether anybody else has ever thought about this. Then you come up with that hypothesis. And when you come up with that hypothesis, it needs to be testable in an accurate way with nothing that could cloud the results. And it needs to be repeatable by somebody else. And then fit in here is also a little reminder of this. I continue to always get a question about peer review. Every time I test, I do. Essentially, it's something to the effect of, how does a scientist get feedback about something? How does a scientist confirm that they have a good hypothesis? How do they perfect their hypothesis? Peer review is usually something you would kind of see before the experiment actually happens, but that's not necessarily a totally black and white every time kind of rule. So if they say anything about feedback, basically anything about kind of scientists getting together to provide some type of feedback about an experiment that's about to happen or just did, that would be peer review. And there's usually a question about that. General science reasoning is great because I had to do a lot of research and studying the patterns of what these questions look like and how they're answered and why they're answered that way. I had to come up with the trends and essentially, just like with everything in my curriculum, I go out of my way to figure out what process they're following. How are they thinking about this? Why are they thinking of it that way? What are the doctrines that we can totally count on? How do they describe certain things and how would they not describe a certain thing? I've done that research for many years. For you, everything in my curriculum is simplified because of that. That's the whole reason that I exist and am successful with this, is that I put a lot of time and thought and study into how they come up with their questions and then their answers. In science reasoning in particular, if you just take my research and my findings and you just organize it and you just make sure you know it and what to expect with it, and you just know the doctrines that they follow and what types of things they ask about, you're good. That's it. It's not like reading where you still have interpretation that you have to do and there's still a perception that could vary between you and the test. Science reasoning is very cut and dry. If you do things and think of things the way I'm talking about them, use some practicality in what I just described, where the first, quote unquote, first step might be different things because of where the question is sitting. But mostly you're going to just go with what this page says, and it's that simple. There is a scientific doctrine that kind of says you should, as a scientist, you should always share your results. And that's how we get this research thing, is that other scientists share their results. The reason that I teach this stuff right here is that sometimes there's a question that says, like, a good scientist would do what? And they might have an answer choice there, like hide their results from everybody. So you might not know whether that would be a good thing or not. And now you know that that's not a good thing, at least from the TEAS perspective, and that's not the answer you want to pick. And that's essentially what you have to do, is come to an understanding and a slight memorization of these concepts and how they're understood by the TEAS. And then whatever questions you do get, they're all going to fit within this frame. They vary quite a bit, but the foundations don't. So this is one area. The remainder of this packet is very cut and dry. You really can go with exactly what I'm saying. You don't have to be as open-minded and interpretive as you have to be in a lot of other areas. These are the 4 foundational understandings. Those are no different than I taught you before. Make sure you are 100% good on the independent versus dependent variable. Make sure that you can describe them, you can picture them. An independent variable is something we change on purpose. It's something we add, or it's something we take away. That is to find out what happens when we add this or when we take away that. There can only be one of them. The example that I use to make sure that we remember there can only be one independent is, let's say that you're having trouble sleeping. And obviously, if you're having trouble sleeping, especially you guys, because you have a million things you have to do every day, you're going to want to get to the bottom of that. And it might be tempting to do like 15 things differently tonight to try to make sure that you get some sleep. But if you do that, if you take sleeping pills and you take a hot bath right before you go to bed, and you do some meditation and you change the sheets to your favorite sheets on the bed, and you do all these different things, if you get a great night's sleep tonight, you're going to wake up in the morning not knowing which of the things you did contributed to that. So to really find out for the long term how to improve your sleep, you have to test one thing at a time. And you have to compare. There's always a comparison going on. You have to compare tonight and whatever you do tonight to a night where you didn't do that and all the conditions were normal. And the premise of a science experiment is we only want to change that one thing, and we want to keep everything else the same. So let's say sleeping pills. We're going to try some sleeping pills from Target. So sleeping pills, if you're going to try sleeping pills for sleep, that is the only independent variable that you can use tonight, or else you're not going to know if you have to have 5 different things or 1. So if, let's say that last night you slept in your white sheets, and let's say you wore your favorite pajamas last night, and I'm saying last night because you didn't take the sleeping pills. Tonight, you need to recreate everything about last night as much as possible. Keep everything the same that you did last night, but take a sleeping pill. That's the concept behind the variables and the control group. I just described a lot of different things we've learned in kind of a combined way, and I'll clarify a few things. That's what you want to be thinking about when you're getting asked this type of question. An independent variable is something we change. So in this case, this independent variable is adding a sleeping pill, taking a sleeping pill. So our control group is when we don't do that, and our experimental group is when we do. So what would the control be in the case of an experiment to see if sleeping pills improve sleep? The control would be no sleeping pills, but everything else the same. Same pajamas, same temperature in the house, same sheets on the bed, laying in the same position, whatever you can come up with. There's hundreds of things you'd want to make sure you didn't change. That's the control group. So control group is a good way to say whatever normal would be, or whatever it would be without the variable added. Without the sleeping pills, what is our sleep like? With the sleeping pills, what is it like? The experimental group is with the change. If there's no control group, there's no way to know if your experimental group did anything at all. Because, and in the case of sleep, that's a hard one to think of this way, because you probably at least attempt to sleep and hopefully do sleep every night. But imagine if you had never tried sleeping at night. So then you wouldn't have something to compare to, right? You would take a sleeping pill, but if you don't sleep normally at night, then you don't know if that's better or worse than what it would have been without the pill. And so what you're looking for in all of these exercises that are coming up with all of these variables and control groups and all that is that. In some cases, there isn't exactly a control group that you can identify. And in other cases, there is. If there is kind of no normal, or if they don't give you any way to identify what normal might be, then there might not be a control group. The dependent variables are the measurement. Every single science experiment must have a measurable outcome. You must have data in order to say a sleeping pill. So let's say my hypothesis is taking 1 sleeping pill at 10 p.m. will improve my sleep. And to make an excellent hypothesis, you'd want to be a bit more specific. Maybe you say, I won't wake up, or instead of waking up 15 times, maybe I'll wake up twice, whatever. But if there's no measurement for that, then we can't show that outcome. So you can't wake up in the morning and say, yeah, I think I slept better. Yeah, I think I did. Because you've got to be able to present this to another scientist. So what you would say instead is, with my control group, when I didn't take sleeping pills, I woke up every, and you'd need several nights of this. Let's say we wake up an average of 15 times. And let's say that with the sleeping pills, and again, we'd need to test it several times to be sure, we wake up an average of twice. That is a measurable dependent variable. And the way that you can phrase that to remember how your variables fit together is with sleeping pills, I wake up less during the night. And how many times I wake up during a night depends on whether I took a sleeping pill or not, or whatever you're testing. How much this plant grows in a 1-month span of time depends on how much water you give it, or depends on whether you give it food or not. So you've got an independent that you're changing. You've got a control group where you're not changing that. you've got a period of time or whatever, and then you've got an actual measurement that you're looking for. The TEAS is very good about not having dependent variables that sound very relative or that sound like it would be some form of an opinion. And what you'll notice, I mentioned this in the other class, this probably sounds familiar. In some of the exercises that I give you, I don't write a lot of my variable exercises because I can provide you a lot more if I just get them than if I have to sit there and come up with the creative stuff. A lot of times we will have answers on the dependent variable that sound kind of relative, like, you know, how well you sleep. With a sleeping pill being the independent variable, the dependent is how well you sleep. Well, that obviously sounds kind of relative and opinionated and very hard to pinpoint. That's not a measurement. That's not, I woke up 15 times in my control. I woke up twice in my experimental group. The TEAS is good about making sure they have numerical backing. So you'll always find, if you can get through my exercises that I give you on this, you will always find that it's pretty simple to get through these on the TEAS because they're very on point with what they give you. They give you all of the information. They give you a very clear independent and a very clear dependent variable. It doesn't sound relative. It sounds numerical and accurate and reliable. And then that just makes this a little bit easier. The page right after this talks about improving an experiment. We had a great conversation about that in Science Reasoning 1. We won't have it again. These questions are being pulled back a bit right now. There's not as many of them showing up as some of the other general science. Again, they're not gone. You do need to be able to do these. The only thing I want to mention about this, if you do not remember exactly how you choose an answer for how to improve an experiment, make sure you go back to Science Reasoning 1. You must be able to say, here's how we would improve this experiment. That's something you definitely need to have a process for. And we did that process in Science Reasoning 1. What I want to point out in this class is something that can be done in just about every instance to improve an experiment is to have more trials. And they might say it that way, or they might say, they might describe it. So you might know what the context of the experiment is. And they might say, repeat this more times. They might say, expand the size of the groups. But you can always assume that the more experience you get with something, the more sure you can be. So the sleeping pill example is great because we talked about that in a very, very small scale, almost non-scientific way. I just basically said, well, if I'm not sleeping well, I'm going to test this. When in reality, how do we know if a sleeping pill works? We want to test it with lots of people, not just me. And we want to test it lots of times. You cannot take a sleeping pill tonight, get some good sleep when you haven't been sleeping well the last week, and be absolutely certain that that pill is what did it, right? So you can't be certain of that until you test not taking sleeping pills and then taking sleeping pills, and you test each of those many, many, many times until you eventually can say, every time I take a sleeping pill, I wake up 1 or 2 times. Every time I don't, I wake up 13 to 15 times. You need more than one instance to be able to actually be certain of that. And ideally, you would want more than one person to be testing this in the same manner that you are. More trials can sound a lot of different ways. We're not going to go through all of them. What we're going to go through is what to be careful of. We have the control group, right, which is where we don't apply the independent variable. We leave things, whatever would be considered normal, we leave it normal, right? And then the experimental group is where we alter the independent variable. We mess with the variable. We add a variable in, or we take something out. We do something to find out what its effect is. These groups, They should both be groups. You should never just test something on one person or one plant or one anything. It should always be a group. The groups need to have as much diversity as possible. If there is diversity to apply to the situation, you wouldn't want to test everybody on sleeping pills that's female, but not test any males if possible, because that's not giving you a very good representation, unless you're actually saying, I'm testing sleeping pills and how they affect females. If you said that, you would want to make sure you didn't have males. So it depends on the context. And again, I'm not going to try to go through every one of these because there's a lot of context, but they give that to you. Factor in whatever that is. Sometimes they're very general with the description. Sometimes they're extremely specific and they say, we're only testing females between the age of 22 and 25. They give you that much, it's going to be very narrow as to who's in those groups. If they say people, then we need to make sure we're representing different ages and different genders and people who live in different places and all these factors that would affect what the outcome is. These groups need to be even. You do not want to have more people that take the sleeping pill than don't, or vice versa. You want the same number. So if 50 people are going to take that sleeping pill, 50 people need to not. If 10 plants are going to be given a certain kind of water and then measured for height, 10 plants need to be given regular water, given normal conditions, and measured for height. So the groups need to be even. So yes, it's always true that adding more people to an experiment that's studying people's response to something is good, but it's not good. The positive influence of that is overwritten if we cause an uneven set of groups. And number of trials, again, can be said a lot of ways. It can be said that way. It could be said, as having more plants. It could be said as doing it repeatedly, doing the experiment several times over. Just make sure it's always even. There's an example coming up where they give like several different kinds of salt water, like different concentrations of salt water, and there's several of them. It would be great to have more plants getting each of those, but it has to be even. We don't want to give 10 plants the highest concentration and test 10 there, but only test 5 with normal conditions. Generally speaking, and I still want you to do what we did in Science Reasoning 1 and have that process in place and have an understanding of the 3 examples I gave you in that class. But once you're good on all that, and hopefully you already are, then you can also keep in mind that more trials is a simple, universal answer. It's very often, if not always, the answer in the questions that are on the TEAS. In one way or another, trying it more, having more people involved is typically how we improve an experiment. And I did mention that in the previous class, but I've had some feedback fairly recently that kind of told me I must not have emphasized that much because I'm getting a lot of people who don't have that part of it in their thought process, and then therefore they struggle because they feel like they see things that are very different than what they saw when they practiced. They can be tremendously different. Every experiment has a lot in common, and we have to use the common ground that applies to all experiments to be able to say what the best way is to do it. I put a ton of practice in here for you, and I went through and made a key to make sure that there's nothing in here I don't want you to do because it's confusing or off pace with the TEAS or something. I didn't really find anything I hated. So you can do all of these pages of these variable exercises, and I will have a key for it. Again, and I said this a minute ago, a lot of them have a kind of relative sounding answer. That's just how it is when we practice for this. There are several examples in your original packet that are not in this one that give you actual test content rearranged. None of them are exactly what they are on the test, but a lot of the scenarios are kind of similar in that first packet. These are not. I didn't write these. I did this to give you practice. I've said this a million times in the course of all your lectures. You have to have a strategy and a process and a system that you use, and it's okay to have certain things memorized, like knowing the fact that trials is almost always going to be the golden ticket to a better experiment is a really good thing. It saves you time. It saves you energy. It maybe increases the likelihood of your accuracy, but you also cannot replace good old-fashioned practice and good old-fashioned working these thought processes and strategies. So we really just want to work as many things as possible, even if they wouldn't come up on the test. And then after that, we want to make sure that any simplifications like that just make it so much easier right off the bat are also being factored in. I'm going to pick these kind of randomly. I didn't pick ahead of time like I often do with which ones I want to go through. Let's do this first page, and then we'll maybe skip a couple pages. So the first one says, students watched a cartoon either alone or with others, and then rated how funny they found the cartoon to be. So what I did, I always underline with this. I always try to underline what I think was important. And in the case of one of these questions, you'll end up underlining your variables. So our independent variable is what we change on purpose. And our dependent is what we measure after we do that. So in this case, we're going to change whether they are alone or whether they are with others. That's kind of a weird sounding independent variable. We usually get a nice one-word answer, but on some of these, you're going to have a little bit more of something like this. So one of our groups is alone, one of them is with others. And then rated how funny they consider the cartoon to be. This is what I mean when I say the TEAS would not consider how funny, I'm going to put quotes around it because that's the way I'm thinking of it. They would not consider that to be a strong dependent variable. That's not, you and I can't both do this experiment and do the results in the same way. But a lot of practice is going to look that way. It's actually going to help make the test a little simpler when it's that way. The next one, a comprehension test was given to students after they had studied textbook material, either in silence or with the TV on. So our independent variable, the changes that we applied are in one group we applied silence, the other group we applied TV. This did a terrible job of actually giving you a dependent variable. They actually totally did not give you a dependent variable here. They said comprehension test. They did not say anything about the score of a comprehension test. That's what they meant. So what I have as my independent variable is comprehension test score. They never said score, but they should have. And the TEAS would not have let that happen. So what I wrote next to it, what you'll see on the key when you see it, is they didn't do a good job of specifying that there's a score, but that is what we would need to measure. And some of these, you may fill in something a little extra like that. And that's good. That allows you to have the thought process instead of you just programming yourself and kind of memorizing how to do this. You would, hopefully you would think of that. You would realize, well, they could have said that better. You know, it could have been more numerical and more accurate, but ultimately, you know, it's close to something that they did say. This last one, some elementary school teachers were told that a child's parents were college graduates, and then other teachers were told that the child's parents had not finished high school. They then rated the child's academic potential. There's a lot going on in there. And these worksheets have really weird spacing. I apologize for that. I don't know why they have this weird spacing. Don't worry about the fact there's this big space here. That's not saying that these are separate. It's just oddly spaced out the way that they typed it. My independent variable is what the teacher was told about the parents. Again, not super scientific, a little bit relative. You might have been more specific here and said like told they were or weren't graduates. But it's ultimately what the teacher was told about the students' parents. About the parents. That's your independent variable. What we're changing is whether we say this person's parents are college graduates or this person's parents did not finish high school. The dependent is going to end up being how the teacher rates the academic potential of the kid. So there's kind of a lot going on with that. And if you get close on these answers and it's a little complicated, but you got the general idea, that's great. It's not going to be this weird and fuzzy when you're on the test. Like I said, these exercises will make the test look very cut and dry and nice and simple. So ultimately, you're looking for what is the numerical thing we're measuring. Again, this is not numerical, or I don't think it's numerical. I don't think they're using a scale that's numerical. I think they're just using a sentence. Oh, I think this kid has got a lot of potential, or not a lot. Again, that's not super scientific, but basically the numerical element, or the measurable, I should say, element, what they seem to be trying to measure is what does the teacher, after they're told about the parents of their student, what does the teacher think about the child's potential? Go ahead and pause in a second after I tell you what to do while you are paused, and do just this very next page. So pause and do this page right here. Then we're going to skip a page that's going to be just for you to do on your own and use the key for. And then we'll do one other page that's upcoming. And then the rest I think I will leave for you. So go ahead and do this page. It's basically number 4, 5, and then 6, but they have it labeled as number 1. This last one is like a fill in the blank kind of thing. You guys know that the TEAS does not have fill in the blank or paragraph or anything like that. But this kind of gives you a chance to think through it. That's the goal of these types of exercises, and there's more of those. Do your best on this page. I'm going to give you the info right away as soon as you're done. Anyway, pause right now. Come back when this page is filled out. I am now right this second going to start the answers to that. So pause if you haven't. Number 4. So the independent variable should be stress management program or not. Did they take this class or did they not? And you might think of or not kind of in parentheses, or you might have just said stress management class. They added a stress management class to their experimental group. The normal in this case, so thinking of normal, thinking of what your control group is, normal would be probably not having a class over that, because I don't think most of us work somewhere where they do that. The dependent variable is the number of sick days. That's one of the best dependents we have seen so far, because that's a countable, testable number. Number 5, the format would be the independent variable. So there's textbook is one group. There are 2 experimental groups in this case, and that is the textbook versus interactive format on a tablet, computer, whatever. And then final exam marks was the way that they said this. If you said score, that's great. That is numerical as well. So they gave them one or another way of studying something, and then they took their score into account as the measurable outcome. And so the statement we could make about number 5 is the final exam marks depend on the format of the education in the first place. The last one wants you to come up with the experiment, and there's several more of those coming, and I want you to not put immense pressure on yourself with these, because these are out of the TEAS format, but do some thinking. See if you can figure out what is the normal, what is the control, what is the variables, how can they put this experiment together, but don't go crazy. You don't need to design a perfect experiment. You don't need to put all the controls in place and all that. So what I said about this is their control group is no social media. The reason I say that, I'm just going to fill this in down here, not on their weird lines. The control is no social media. If you actually read the heart of this, you could think this is going either way, because it says using social media, expressing yourself. When you think about social media in context of a social experiment, so if you think about exposing people to social media and then experimenting on them, there's a lot of things you could find out from social media. There's a lot of things people lose because of social media, and there's a lot of things people could gain. So we could do an experiment about like someone's knowledge of current events. And we might find that people who are on social media maybe have more knowledge of current events. Mind you, they would also have more knowledge of current events that were fake and made up. But you have to be careful in your context here, because social media in and of itself is not a good or bad thing, and it's not something that takes you in just one direction. What they're saying here is that the more time, this is their hypothesis, the more time you spend on social media, the less you can express yourself. So that would mean we are trying to add social media. Our independent variable is to put social media in front of someone. And then our dependent, our measurement that we're trying to do, is expressing themselves. And again, that sounds relative. There's not a numerical part of this, because you'd have to kind of have somebody's opinion of whether they express themselves well or not. But their hypothesis is the more time you spend on social media, the less you're able to express yourself verbally. The control group is no social media. How can you express yourself if you've never been on it? The independent variable is social media, because of the fact they said the more time, the less able. There's probably multiple experiment groups here. And you did not have to have come up with that. If you did not come up with that, that is okay. But I'll give you the whole thing. I'll give you as much as I think of, and then you can see if you can come up with that on some of the future questions. The reason I say that is they're saying the more time you spend, meaning they want to test someone who's not on it at all, and that's their control. That's how a normal everyday person could express themselves. And then they want to get somebody that does a little social media, a lot of social media, and a ton of social media, because they're saying the more time you spend, and they're probably going to put that in categories, 2 hours a day, 10 hours a day, 20 hours a day. How do we see those differences? They're trying to say as social media time increases, at the very same time, social expression decreases. That actually relates to something we're about to talk about. If I remember, I will come back to this as that example. The effectiveness of their expressing of themselves is what the dependent is. I know that's not numerical, and that makes it tricky. Hopefully you came up with at least the independent and dependent variables here. Hopefully you did come up with the control. Remember, there is going to be certain situations where there isn't really a control. I'm going to show you one of those. This page right here. So I skipped a page and went to the very next one after the one I skipped. Again, go ahead and pause. Do all of these. I'm going to show you on this worksheet that occasionally we can't really find a control, and then sometimes we can. And I'm going to tell you that up front, so that if you figure out on one of these that you're feeling like there isn't an obvious control, just write down comparative if you feel that way about one of them. Comparative meaning we have several experimental groups that we're going to compare at different levels, but maybe there's not exactly a normal in the first place. You'll see what I mean, I think, when you run into it. Go ahead and do this page. Don't worry too much about control groups. You do not need to be an absolute expert on control groups. The key is you need to know what is the independent and dependent variable. The control is good because it establishes that you're understanding how this works, and that's going to help you eliminate certain things on really hard answer choices. But we're not trying to learn about control groups. So don't put a ton of pressure on yourself with that. Put the pressure on the variables. Pause me now. Take however much time to fill in just this page 1, 2, 3, and 4. And I am now going to give the answers to that and discuss. The very first one, the type of rose bush, was the independent variable. Different rose bushes are grown in a greenhouse for 2 months. The number of flowers is counted. So the number of flowers is our count. We are testing basically based on which type of rose bush it is. Does it grow more or less flowers? Can we rank them by type and then how many flowers? This is the one that didn't really have a control. The reason it doesn't have a control is these are all different types of rose bushes. What's a normal rose bush? They really gave us no context to know that, right? So most experiments do have a control. In this case, this is comparative. And that's where I kind of get that answer when there's not one, is it's comparative. We're comparing, you know, type A and B and C and D, and they're all going to probably have varying levels of flowers. You're going to have a whole bunch of each type. You're going to need 50 of this type and 50 of this type. You're going to make sure they're even, 50 of this type, 50 of this type. You're going to average it all out. And ultimately, you're doing a comparative experiment where when you get to the end, you find out, oh, you know, rosebush type A generally on average grows a lot more flowers in a month, or in 2 months, actually, 2 months. And then B grows by far the least number of flowers, and so on. That is comparative. There's not a normal versus not normal. They're not trying something out. They're comparing for things, and there is not a baseline. And you might have had in 2 months here. There's often a time frame. It's good to put that in your dependent variable because, again, it's just better comprehension. But again, don't put too much pressure on yourself with that. Number 2, the independent variable was salt water. And more specifically, it was the amount or the concentration of salt in each. This experiment has several experiment groups, but it does have a control. There is a plant that receives pure water. And we're going to call that the water plant because I happen to write water first. That's what we would assume is normal. Usually they'll stay in a context that's relative to normal life here. So you probably are aware that usually you water a flower with water rather than salt water. So it should stand out to you that that 4th plant getting pure water is the normal one. That's what we would normally do. So we're kind of testing 2 things. We're testing the effect of there being any salt in the water, period. That's a comparison to what we would consider normal, but also we're testing at different concentrations. So each plant that's in an experiment group is going to get a different amount of salt. And then over a 2-week period, the height is measured. So in 2 weeks, we measure the heights of a normal situation and then each concentration of salt. It is comparative, but there is a normal, so there is a control group. 3, the independent variable is the level of humidity. We add or remove, increase or decrease humidity. And then we measure the height, I'm going to abbreviate that, of the tree. And we do that in 1 week. The control on this one is the tree that's outside. So again, they made it fairly obvious. In fact, they actually used the word normal this time. Normal conditions. There is one tree that is going to be our baseline for how a tree would normally behave. And then we're going to have different levels of humidity intentionally applied to the tree to compare that to the normal. Number 4, independent variable is the extra water, the different amounts of extra water. Again, there's a few experiment groups. There is a control group, and it's the tree not getting extra water. So again, we have comparative. There's a few different experimental groups that are getting different amounts more than what would be considered normal. We're going to measure the height of the plant, and we're going to do it each day in this case. The rest of all this crazy stuff is for you, and it's several pages. Keep practicing on that. Again, you don't need to put a ton of pressure on yourself to be some kind of scientist, but definitely the independent and dependent should be jumping right out at you the more you practice. And then understanding just, is there a normal? What does that look like? That will help you with improving science experiments and some of those harder things. This next part, I went crazy on this. I'm not going to lie. I went absolutely crazy with these graphs. I did this because I have an OCD with this type of thing, where I wanted to represent everything. You do not need to worry about these graphs. Basically, I guess what I would tell you is when we're done discussing this and you're kind of going through on your homework run, understand each of these 9 graphs, and that is it. So it should make sense to you. If you understand birth and death rates here in a minute, each of these graphs should make sense to you. You do not need them memorized. You do not need to be able to build a graph in your head. Nothing like that. Some of you will love the graphs and you will want to do it that way and picture it that way, and that will help you get those right. That's fine. But the fact there's 9 graphs on this page makes it look seriously complicated. This is the least complicated thing you're ever going to hear from me. Very select little group of questions considered general science about decreasing and increasing populations. And I have those right here. And there's a few terms that we talk about when we talk about this. So birth rate is how many births there are in a particular population in a period of time. Usually a year is how they think of these. Death rate, obviously based on the definition of birth rate. A death rate is how many people die in that same period of time, in that same population, same period of time. And then the one you might not be as familiar with here is infant mortality. That's not really something, that is something that happens in America, but not to nearly the extent that it happens in a developing country. And there's basically developed and undeveloped nations, and that's, they don't really talk about that anymore. They used to with these questions, and now they kind of don't. But there's developed and undeveloped nations. A developed nation would be any nation that's basically, an undeveloped would be what you would call a third world country, is the kind of slang way that we refer to them. And then developed would be anywhere that there's like a pretty good system of society and government and economy and all of that. Healthcare being the big one. Infant mortality does happen. There are definitely deaths of infants in many instances in our country and every other country. But when we say infant mortality and we're talking about a rate of infant mortality, we're talking about countries that have little to no healthcare system, and they're not able to fight things like pregnancy of women who have HIV or pregnancy of women who have something that ends up killing the infant either while she's pregnant or maybe shortly after the infant is born. So when we say infant mortality, which is just very simply deaths of infants in a population, would see this in a developing, when I say developing nation, that kind of conflicts with how I just used those words, sorry. Developing, if you would refer to a nation as developing, they are not developed. So another way of saying developing is undeveloped. They kind of sound like they conflict. We would see an infant mortality rate probably in a country that has a high death rate. Maybe not. In any given one of these questions, you could see all 3 of these given to you or 2 of them. And essentially the question you're always going to get asked is kind of the same, which is the population growing or increasing? Is it staying exactly the same, or is it decreasing? Just very logically, practically think of this for a moment. What would the birth and death rates look like in each of those scenarios? If the birth rate is a lot higher than the death rate, more people are coming into society than leaving. That is an increasing or growing population. A decreasing or declining population would have a higher death rate than birth rate. A lot of times we would see this in a society that has a high rate of infant mortality, because normally, since more and more people walk the earth every year and more people have babies every year, you would typically see less people dying, like elderly people dying, than you would see people having babies. There would typically be more babies being born than old people dying. And so a society that has a high infant mortality rate has this extra factor that's really pushing their death rate up. And if the death rate exceeds the birth rate, then there are more people leaving the population numbers than coming in. All of these graphs, I'm not even kidding. You're probably like, are you kidding me right now? All of these graphs are just showing you just what I just said. I'm not even kidding. All of this visual is just for that simple thing. You'll see that I have titles. I'm not going to go through all of these. I have stagnant or stable. That would mean that the birth and death rates are about the same. They could both be increasing. They could both be decreasing. They could both be staying exactly the same. But if the death and birth are equivalent to each other, they're progressing at the same rate, you're not growing or declining. And that's what this last row shows. The middle row shows regressing, decreasing, declining is another word for it, population. You need a higher birth or a higher death rate than birth rate. So they could both be climbing. Like this first graph shows that there is a slight increase happening with deaths as the year goes on. And there's a slight increase happening with births as the year goes on. But deaths is at a higher number. There's 1 million people dying every year in this made-up society. There's only 500,000 being born. So we are declining. They're not going to ask for a number. They're just going to ask growing or declining. Whereas here, you see them cross over in the middle. So this one, and always assume, I guess, that each of these graphs is showing 1 year of time. So in this middle one right here, we started out actually with a higher birth rate than death. So at the beginning of the year, we started out with 1 million births happening, or on pace to 1 million births and only 500,000 deaths. But the death rate grew and wound up here at 1 million or over 1 million. The birth rate declined as the year went on, or however much time, and we wound up down here at 500,000. And numerically, we actually end up in the same place with this graph that we did with this graph. We just got there in a very different way. So there's a lot of visual representations for this. You don't need to have any of them memorized. You don't even need to be able to picture one of these graphs. I have these graphs in here because I have a feeling they'll eventually go that route. They know that graphs scare people. And so if they show you a graph of this and you know what the basis is, and you know that, you know, your wacky, crazy TEAS instructor just like sat here for 2 hours just making graphs that show random scenarios off the top of her head, then it would be easier for you to know how to read one if they throw one in front of you. So feel free to look at each one of these. Do not memorize them. Do not stress about them. Nothing like that. If you don't understand the graphs or you don't like the graphs, stay away from the graphs. All you need to know is this. If you got more births than deaths, you've got growth. If you've got more deaths than births, you've got decline. If you've got high infant mortality, you could still be growing as a population. Just to be clear, you can have very high, ridiculously high infant mortality and still have a growing population. But it's a lot less likely. It is a lot more likely that we see a regressing or stagnant population if we have high rate of death in infants. That's all you need to know there. I spent a ton of time on these graphs, but I really just did that because I'm crazy. This next page is kind of some more, these are pre-made graphs that I didn't make for kind of the same thing. This one actually shows the growth curve. So you're able to see the final result and how it got there with the birth and the death rates. This one is showing Japan. Japan is actually one of the only developed nations ever in the history of the world who just recently, and by recently I mean 2005, which means I'm getting really old, they just recently started to decline in population. There are so few births happening in Japan versus how many births were happening 10 years ago that they are now actually declining in population. Random fact more so than anything. The next page is about data interpretation. Again, this is a lot of notes. I already had these notes. These were totally prevalent on the TEAS 5. You don't need to go crazy with this. I'm going to point out a few important things. You are more than welcome to read through this whole thing. There's a couple of key things you need to know. One of them is you need to know essentially whether you have one type of data or another. And that is right here. You kind of, sort of, oops, hold on. It's actually there. It's the first 5 terms. Those all go together. Those are going to be types of data. You don't really need to worry as much about the second 4 of those. And then types of graphs and their usages. So you could be asked a question like, This scientist wants to do an experiment over this, and then they want to show these results about this. What kind of graph do they use? We're going to keep that incredibly simple because it is incredibly simple. And this will allow you to say bar graph, circle graph, line graph. Types of data. What's really important in types of data is this first two, quantitative and qualitative. We've actually hit this quite a bit in the last 20 minutes. Quantitative is a measurement that is numerical. As you now know, we like that. We really like that. It's really hard to base an experiment on something that is not quantitative. Qualitative is sort of the opposite of quantitative. Quantitative is easy to remember because it's quantity, which is numerical. Qualitative is to describe a quality. So to say, you know, we try these different weight loss medications and then we look at these people and we say, wow, that person looks really good and that person looks fairly good. That's qualitative. They look good or they seem healthy. Versus the numerical in that instance would be here's what their weight was and here's what it now is for each one of them. So understand that. That's all you need to understand there. Empirical data is everything that is observed. And this is a weird technicality. You don't need to memorize this. Just understand it. Empirical is a weird combination of both of these because when you think of an observation, you would think of qualitative, like height or weight or look good, look healthy, looks very green versus doesn't look very green, whatever. That's what you would think of when you think of observation. But you actually, when you conduct a measurement, that is done by observation also. So if you have someone stand on a scale, you observe the number that pops up on the scale. So empirical is a weird way of saying both. Most experiments will be empirical when they are finished. Every experiment absolutely must have quantitative data. You cannot have an experiment without that. It does not have to have qualitative. Qualitative is definitely lower in priority and preference. It's not mandatory to an experiment. It's often disregarded in an experiment. And if it is there, it has to be secondary to a numerical property. That would tell you that some of the things that are in your variables practice would not actually qualify for scientific criteria and for the TEAS scientific criteria, but we already kind of know that. Discrete is not a word I want you to know for science. It's a word I want you to know for math. And we've talked about it before, but you might not remember the name. Discrete means that it can only be expressed in a specific value. Continuous can be expressed with any value in a given range. Meaning temperature, you can have, 95.7 degrees or 0.8 or 0.9. And you can have any measurement that fits between a certain, low limit and a certain high limit. Discrete is where there's no partial measurement. You can't have this decimal. Great example, people. And I've told you in your math classes, be very careful because if you have an answer that's in people, so you're trying to say how many people are going to do something in math, if you get a decimal and you're talking about people or cars or anything that can't be represented partially, you have to round it up. So even if I got 11.1, mathematically, we would always think of rounding that down. But if I have 11.1 people, I cannot randomly get rid of this partial person. What I have to do is round all the way up and say, if there's over 11 people, if there are more than 11 people, there must be 12 people because there's not half a person here. That's important to just know that exists. You do not need to know its name. Just know that you have to be a little careful when your answer is in a unit that cannot exist partially. If you have more than 10 computers, then you have to have 11 computers. Even if you only had a little teeny tiny decimal, you can't create that. So you have to go to the next number. Graph types and usages. so there's basically 3 types of graphs. Let me make sure that that's all I have in here. I'm pretty sure it is. Yeah. So there's 3 kinds of graphs. There's bar graphs that look like this. There are pie charts that you have seen tons of in your math classes, and they look like this. And there are line graphs. And you've seen a little bit of line graphs, but not very many. Each of these is designed for a particular thing. And they can give you a scenario in a science question and have you choose how you would show it. I'm going to start here on the circle graphs. Circle graphs show how parts make up a whole. So what we see circle graphs for is things like a budget. You see that on math all the time where it's like 35% of your money should go to housing, 15% should go to transportation, so on and so forth. There's a total budget, right? You make some certain amount, even if it does vary in a month. You have a total amount of money that you can't just magically exceed. You have to stay within that. So a pie chart is designed where no matter what you make this month and no matter how much that might vary from last month, this is going to be the percentages of that money, whatever that money is, and how they compare to each other. The examples I have here, this is leisure activities. So this is saying all of the people who are doing leisure activities all throughout the world are participating in one of these things, and here's how they compare to each other. So what this graph tells you is, wow, 31% of people, which is clearly a much bigger chunk of the pie than any other chunk, choose walking as their recreation. That's what they're trying to show you. What do people do the most of? What do they do the least of? What should you spend a lot of your money on versus a teeny tiny bit of your money on? And they always make up a whole. So you have a certain number of dollars, and this is how you distribute them amongst different things you have to pay for. There's a certain number, in this case, of nurses. So they probably, for this graph here, they probably counted up all of the RNs in a particular state and said, here's the total. There's a certain number of RNs in a particular state. 29% of those RNs work in, this is a really hard legend to read, and that's okay because you don't need to be able to deal with it, work in surgical or general hospitals. And 8%, smallest portion, are in home health. And the second largest proportion are in doctor's offices. And so they're showing you out of every nurse, so every nurse in the state of Texas, for example, is in here. This is how the quantities that work in different facilities compare to each other. So that's what a circle graph does. You don't really see, that I can think of off the top of my head, anything that's a science experiment that would be shown that way. I could be overgeneralizing that for sure, but usually when I think of what we're trying to show when we're showing a science experiment, I typically don't think of a circle graph. I picture circle graphs for all the people that live in a certain city, how many of them prefer the rec center versus the library versus they're showing you how the parts make up the whole. When we take every person, we represent their favorite place for leisure, and we put all the people in one place. You can see that there's more of them that prefer this, and there's less of them that prefer that. There's more that work here and less that work there. There's more money that should be spent in this sector and less money that should be given to this sector, and so on. A bar graph is to show you a comparison of how different things work. Usually a bar graph is not the parts that make up a whole. So very much the way to keep a circle graph separate in your mind from a bar graph is when you look at the whole circle, that's everyone. That's the circle represents a group fully. The circle fully represents a certain group. And everybody's there. There's a total. Out of everybody, here's the way they all distribute. A bar graph is going to show you more of a quantity measurement of some kind. So like here, this is trying to show you the income of different kinds of nurses. So you got LPNs, RNs, practitioners, and anesthetists. You got men and women. You know how to read all this because of reading. And what they're trying to show you here is not how the totals distribute. That would not make sense in this case. So if you compare this to the circle graph about where nurses work that we have on the other page, there is no total for this. We have no way to show a total on this. We're not saying there's 3,000 nurses in this city and here's how they distribute, right? This is not saying anything like that. There's no way to do that and have a whole. So there's no way to have the whole pie and then break it up into sections. This is saying if you're an LPN and you're male, you are likely to make somewhere around like 40,000 a year-ish. And don't worry about the numbers being specific. This is not a great graph for being accurate. Whereas if you're a nurse anesthetist, which is a lot of extra schooling, but it's a great career, and you're a male, you are likely to make somewhere between 150 and 180,000 a year. What they're trying to show you by putting this in a bar graph is, whoa, there's a tremendous difference between the pay of these types of nurses and the pay of this type of nurse. And they're trying to show you that comparatively. They're trying to kind of go for that wow value of look at these immense differences in income. If anyone wants to know more about being a nurse anesthetist, as a side note, a member of my family did that as a career and did extremely well for himself. He did quite a bit better than most doctors. And I think it's really cool. I seriously would have gone into that if I didn't go into education. So if you want to know about that, let me know. An example I saw on my very last test said there's a scientist and he wants to show how much people responded to a certain drug versus a placebo. Placebo is a word to make sure you're familiar with. That's where they give them a pill. So they think they're taking a medication, but there's nothing in it. It's like a dud. It's like they give them sugar instead of an actual med or something. And they measure, that's how they measure drug effectiveness. So everyone in a drug effectiveness experiment thinks they're taking the drug. Even the control group thinks that they are taking it. But the experimental group is getting the drug, and then the other group is getting the placebo. And what you would probably expect to see in this bar graph is if the drug is effective, that the placebo was, you know, this amount of people reported results. So let's say that over here, this is the number of people who report results, the number of people who got results. Here's your placebo and here's your real drug. And again, they're trying to show you a lot more people that took the actual drug had results than placebo. Placebo has a mental effect on it, obviously. So you're not going to see that as 0 because there are some people who have very powerful minds. And if they think they took a medication for blood pressure, they will actually lower their blood pressure because they're so focused on the fact that they took this medication. But we will see a big difference, and that's what they're trying to show is that big difference between those two. Most science experiments, I would say, would be shown with a bar graph. This is the absorbance of one paper towel. This is the absorbance of the other. When you put bars next to each other with measurements, you can see an immense difference from one thing to another. That's usually what they're trying to show. The last graph type is line graphs. There is only one way we use a line graph, and we don't use them very often, at least in the context of the TEAS. A line graph shows a trend over time. A line graph shows, in this case, all the way from 2005 up to 2012, we had 4 types of professors, and we're looking at what does their income do on a very continuous basis for this 7 years of time. Over 7 years. And if you notice, each one of them had a little cut there. So between 2005 and 2006, we can assume something kind of happened with the economy or something. every category started making a little less. And then they all kind of went back to where they were before that. And so in 07, things kind of normalized. And now we're seeing all their trends. And essentially their trends kind of stay around the same number, but they're going down a little, up a little, down a little. If you were in a bar graph right now, you could not find out, oh, wow, what happened in 2006? Everybody lost some income. What happened in 2007? They got it back. What happened over here in 2012? They're making less than they made in 2011. A line lets you see that. It lets you see increasing, staying the same, decreasing, increasing, and so on. That's what you're trying to show with a line graph. And you can only do that if your data is continuous over some period of time. So let's say that we're doing an experiment with plants and we're measuring the height of a plant that's getting different things, salt water and regular water and whatever. If we measure them every single day, then we might be able to use a bar graph, although we don't really need to do that. We're not trying to show a trend. We're trying to show how they compare when it's all said and done, right? When you're trying to compare these, there's two things that are going on here. One of them is they are showing similarly to the bar graph. In fact, we should compare this with the bar graph that we just looked at. They're trying to show you that a full-blown professor usually makes around, 90 to 100,000 versus an associate professor usually makes around 75. An assistant would make less. They would make around 67. And a lecturer who does not have the title of professor maybe makes around 55. So this you could have shown in a bar graph. Just like they did with the types of nurses, you could have made the exact same thing with the types of professors. The reason this made it into a line graph is they measured these people over the course of several years, and they measured every single year. And so they're trying to show you not only that there's a massive difference in these different categories, but also they're trying to show you that they had decreases and increases and decreases and increases as this period of 7 years progressed. We don't see a lot of situations where we're trying to show a trend. A trend is, hey, look, this is increasing. Now it's staying the same. Now it's decreasing. Now it's increasing, staying the same. Now it's decreasing. If your salary has done this, that's not good. Let's say that this is my salary. This is a very different thing that I'm understanding by looking at a line representing my salary for 10 years than if I say, what is my average income versus a tutor who teaches something else or who does their program differently or whatever. A bar graph would compare us. This person usually makes this. This person usually makes that. Whereas a line graph would show how I progress moment to moment. And maybe you also put that other person on there like you did here where there's 4 different people and maybe you don't. So those are basically the 3 types. The next page is correlation. And this is really the last big thing that we're going to study. I know that this class is many hours long. I totally went into this class like I always do, hoping for it to be like really nice and concise and short. I'm really bad at that. Partly that's a personality defect, but partly this is a lot of information. There is a lot that needed to be elaborated on and explained and organized and evolved. There is still, despite the fact that this is seriously probably around 5 or 6 hours of content, there is still a lot we did not cover that you have to go back to your original classes. This is a big section. If you are not trying to score a lot higher than you already scored, or you're not trying to score up into the 80s or into the 90s, you have more potential to not worry about all this than someone who wants to score 95. If you want to be in the 90s or the high 80s, or if you have to make a massive increase in your test score, all of this stuff is important because we have no idea whether they're going to ask you about a bar graph or a correlation or a birth and death rate or all of these other things that we've gone through. We have no way of knowing which 15 questions out of all this you're going to get. And those 15 questions span probably 200 possible questions that are all different. If you study this class intensively and you go back to anything that I told you to go back to from the other classes, you will put a lot of time in. You will put a lot of time in. So if you don't have the time, this may not be where you want to put extra time. But if you do have the time, or you're able to make the time, even if you're on a short time frame, you will ensure 15 points if you can really make sure all of this is good and that you go back to any major thing that I explicitly stated during this review. We are not actually reviewing this. Go back to this location if you want to review it. If there's something I didn't go through and you're great at it, you're probably okay. But again, has to do with how much time you have to put in. Eventually, I will probably re-record this class and try to shorten it. Let me know if you have any feedback on that. Let me know if, you think I undershot anything, overshot anything, if, and it takes a lot of feedback. So it's not like one person saying, oh, you went into way too much detail about this. I can't adjust anything unless everyone kind of seems to think that, because I don't know what you guys find the easiest and the hardest. So as I'm changing all of my curriculum, because I'm changing all of it right now, any feedback you have about, how long we go on about one thing or how much we don't go on about another, any feedback you have about this is pretty easy for me, this is really hard, is great, because I can factor it in and try to put the time in the most effective way. Correlation, again, something from TEAS 5. These are old notes from before. It's just starting to surface again. It's pretty simple. There's basically two kinds of correlation. Basically, there's positive and there's negative. Hopefully you kind of know correlation just as a word, things that relate to each other. The TEAS asks about correlation. The TEAS does not ask about a related concept of causation. Causation is, you got to have some fairly serious info for that, I guess you would say. You have to be able to say for sure that one thing is causing another. That's a cause effect if you want to relate it to reading. They don't really do that on the TEAS. You might see that word. You probably won't. They ask about correlation, which is essentially to say two things relate in one of two ways. That sounds really general. I will get more specific there. There's two ways that something can correlate. It can correlate in a positive direction or a negative. Very simply, and you'll see I've got all kinds of pictures on here for you. First of all, there is zero correlation. Not everything correlates, right? So zero, if they visually show it to you, it looks like this. There's no trend. You can't make a line in it. Zero correlation is like, let's see. I'm going to be really outlandish with my example here. I take turmeric for inflammation every day. It's a great supplement for inflammation. And you study my content every day. What the heck do those have to do with each other? Absolutely nothing. Whereas if I say something more like I take turmeric for inflammation every day, and every, time that I increase the dose of turmeric, I feel better and better and better, or I have less pain would be an easier way to put it. So you need the two things to relate, and typically they do. So we don't see a lot of zero correlation on the TEAS 6. We did on the 5. We see a lot of positive or negative. You'll notice in this picture, this and this don't exactly look the same. And hopefully what you're noticing is this looks like a more certain correlation than this does. What I mean is when you look at where they put the line and you look at where all the dots are the actual data. A correlation is not a causation, so it's not going to fit perfectly on a line, but there's going to be a reasonable suspicion that we can form that there is a relationship between two things. And again, right now, they're not using pictures much, but you might use them to make sure that you can do the descriptive style that they are using. This one is less correlated, but there is a correlation, because if you took the line off and you looked at the way these dots look, they do look like they're kind of doing this, even though there is some space. This one looks like it has a really good correlation. They're fitting real tight, close to the line. What's important is the difference in positive and negative. If you've done my algebra class, and you most likely have, hopefully you're actually recognizing right now, oh yeah, because a negative graph goes this way and a positive graph goes that way. And we know that. And visually, that's how they work. A zero does not have a line that can be formed. There's nowhere you could put a particular line because these look very random in their spacing. Versus this one, you can definitely see has a positive correlation. Why? Because every time that the auto accidents right here increases, every time you get in another accident and your record of accidents increases, your insurance cost increases. So what I just said was increase, increase. When one thing increases, another thing increases is a positive correlation, and visibly it looks like a positive graph. If something decreases and something else decreases, that is also positive. That would also look like this. It would not look like this. Again, hopefully you have some experience with graphing if you are going with the visual part of this. In this graph right here, one of the axes is increasing, the other is decreasing. In this one, they're saying when mileage of a car increases, its value decreases. So one axis is going up while the other is going down. So I'm going to write on this next page just because of having space. There are two ways that we might see a positive correlation. They're going to do this in words. And it doesn't matter what the subject matter is. They're going to say when blah, blah, blah increases, blah, blah, blah increases. Or when blah, blah, blah decreases, blah, blah, blah decreases. If we see increase and increase twice, we see them in the same sentence. One thing increases and so does another. That is positive. If one thing decreases and so does another, that is also positive. So if we have two things behaving in the same manner, they have a positive correlation. They are correlated to each other. Negative correlation is going to say such and so increases while such and so decreases, or vice versa. Decreases, increases. It is really that simple. They will describe it. They'll say which of these is a positive correlation. If they ask for positive, you're either going to find this one here or you're going to find this one here. And you're not going to find the other one because those would both be good answers. And then you're going to find that all the other answers are a mix of increase and decrease, which is negative. If you ever forget which one is which, tricks of the trade, and I'm going to emphasize this more in future curriculum, you'll notice that if you kind of remember how the category works, you'll be able to tell that 3 of the answers are working one way and the 4th answer is working another way. What I mean by that is if you can't remember which one is positive and which one's negative, let's say that they have an answer there that says decrease and decrease, and it would be very reasonable for someone to think, wait a second, is it a positive correlation when it says decrease and decrease, or is that negative? What you'll notice is all the other answers will say decrease, increase, increase, decrease. And so those are the same, right? And you'll recognize that even if you can't remember the names, you will recognize that these are the same. They're the same category. They fit the same description. Well, you can't have 2 right answers, right? So if you're trying to find a positive correlation and 2 of your answers match, then they can't be the answer. Now, the one more answer, because you're sitting there thinking, but there's 4 answers, would be something like something increases and then something else stays the same. because that's the other thing. Zero correlation is for one thing to change and the other to stay the same, or both things stay the same, or something like that. So this, anything that says stays the same is not going to be positive or negative. So you can get rid of this because you know that's not a positive or a negative. And then if you're having trouble remembering which is which, look across your answers because you'll find that two of them are doing the same thing as one another. And then the other one is doing the opposite of what all the other answers are doing. And that's the only one that can be right because it's the only one that's unique. So if you can't remember whether or not this is a positive correlation, the fact that there's nothing else behaving the way this is, but these two are behaving exactly like each other, will give you the answer. And you can use that strategy in a lot of ways in a lot of places. Last couple things here. I'm not going to go back through these pages. These are the same pages that I did in the other packet. This is from Science Reasoning 2. This is very, very, very simple. Most of you guys have not even put an ounce of thought into this, and you're doing great with it. So make sure you know the equipment. I really didn't fill anything in on the on those note pages. I really didn't say much about what you use them for. So you do have to go to the beginning part of the Science Reasoning 2 lecture if you don't know what they are, but most likely you already took notes when you did take that class and you already have notes on that. It's just in your other packet from your other class. They're not hard at all. You just probably have to hear it once and you're good to go. One thing I am adding, and this is the very last thing, this is the only remaining thing that is new, is to be able to read the measurement on a triple beam balance. This is also going to be represented in my two newest mocks. So if you've taken one of those already, you have seen it. When you read a triple beam balance, it used to be that the question was just, how do you measure weight in a lab? And you just had to say that you would use one of these. Then they started putting a question on there where they actually ask you to read it. The only reason anyone would have trouble with this ever that didn't know about it is it seems sometimes like it's in the wrong order. And actually, what's really weird is the examples that I just so happened to pick are actually in order. And that's really strange because they typically aren't. So I'm going to actually draw one down here. Triple beam balance. You can infer from the name triple that there are three measurements. There is a measurement that's in the hundreds. There is a measurement that's in the tens. And there is a measurement that's in the ones. Yes, a couple of examples that I have here actually have a fourth one that's like a decimal. That won't be on your test, but it's self-explanatory so that you can do it for practice, which is like this one. The reason I put these in a weird order right here is that's how I usually see it on the TEAS. So they'll have the hundreds up here. And so they'll have like 100, 200, 300, 400, 500. And then, you know, like they show right here, you'll be able to see that the balance is pointing to one of these particular numbers. In this case, let's say it's 100. And then there'll be, usually it's kind of out of order. So like the next one down won't be the tens, it'll be the ones. And it'll make you wonder if you don't know what you're doing. Oh, do I put this number next or do I put the other number next? You do this the way you would do place values in math. Let's say that the ones, we've got 1, 2, 3, 4, 5, 6, 7, 8. And let's say that our balance is right here. It's pointing at this. And then the tens is going to be like 10, 20, 30, 40. So they all look different. And that's an intimidation tactic, I guess, that they're using on the TEAS, even though this is the way triple beam balances do look and work. And they kind of have them in a weird order that makes you wonder, how do I put these together? Because clearly we have three totally different numbers. You're certainly not going to just put these numbers together and have a ridiculously huge number. So you're not going to be like 100, 350. They will give you an answer that looks like that. And it is tempting if you have no idea how to read one of these. That's not how we do it. What we do is we build the number. My recommendation, I said this in a mock that I just recorded, is to do it verbally, to actually say it to yourself. So find your hundreds and write it down. In this case, it's 100. And then find your 10 and write it down. So that's going to be down here. Your 10 is 50. And then find your 1 and write it down. You've got them written separately. You need to combine these into one number that's in the hundreds. When you read this to yourself, you'll hear what the answer is. 153. 153 is written like this. That's how we get that measurement. Very simple, but you've got to know that's how you're supposed to do it. And you've got to be prepared for the fact they may have it out of order. They can have it out of order any way they want. They can have the hundreds down here and the ones up here and the tens here. It doesn't matter. And it doesn't matter because you can recognize how the numbers fit. So find the one that's got 3 or 4 digits first. They could have a thousands in there. Find the one that's got 2 digits. Find the one that's got 1. Write them in descending order. Write your 100, write your 10, write your 1. And then read them together and form what you say, form the number that you say. That is your reading. There are 4 practices here for this. There's also 2 different mock tests that have a practice that also gets explained in case that was the first place that you saw it. So you'll see an explanation there too. So that concludes the intense review. Make sure that you know how to approximate what the metric measurement of something would be. I did not talk about that. Make sure that you know the basic lab equipment. How do we use certain kinds of microscopes for certain kinds of things? Would you use a flask or a dropper pipette? That kind of thing. Those are all simple enough. I'm not going to put time into them. Anything I went through that you felt good about already and I didn't tell you anything new, or maybe I did, but you were good with everything prior to that, you don't have to go back. Anything you think you need to get a little more on or you need to remember a little bit better, please do, if you have the time, go back to Life Science 1 and 2 or Science Reasoning 1 and 2. Keep in mind, Science Reasoning 2 had a whole bunch of overflow from Life Science. When I redo the curriculum, that won't be the case. So you may not have seen that. But if you're somewhere in the very early part of 2019, that is the case. So like enzymes, I've had people say we didn't go through enzymes. We did. We did it in Science Reasoning 2 rather than in Life Science because of how much time Life Science takes up. So once you've gotten a chance to review your original content wherever that is necessary, as well as the new content, and then done your mocks. So your mocks will definitely help you ensure that you know where you're at. Let me know if there's anything you need to know more about, any questions or clarifications. This is not the most points intensive. It does add up. This is 15 of your questions out of 150, which means that these 2 things combined are 10% of your test. If you don't have time, and especially if you don't have time and you're struggling with anything that's in the anatomy, physiology, or reading, put your time there and then kind of come back to this. This is lengthy and extensive and ridiculous, and I probably will try to shorten it at some point. But the reason it's like that is because there is just such a vast spread of possible types of questions in a really small section, and there's no way to know which 15 you're going to get. There's probably 10 different possible combinations that are quite a bit different than one another. The best thing you can do if you've got the time and the focus is to just know all of this crap. And if you don't have the time and focus, remember that this is 10% of your test and anatomy is a little under 30% of it. So you got to put your time in the biggest categories. The biggest categories are anatomy and then reading 1, 2, and 3. And then you can kind of circle back. Definitely the new mocks are going to show some of this personified a little bit differently. You're probably doing those as well as you're doing this. Let me know if I can help anywhere, and I will clarify anything that I can for you. I will send out a key if you're ready for it. Let me know if you're ready for this key. I will have that to send out so you can see where you're at on some of this. And then let me know if there is something I can help with or clarify. I will see you guys later.